Hi guys, I am so excited because today we're finally learning the derivative of a function. I love this note. Honestly, it's just so much fun and you're going to love it too. I know it. Okay, so this is the last day we have to use limits. After this, we get to use limits to just find derivatives and life is going to be a lot easier, but this is kind of the foundation for understanding all of derivatives. Hope you're excited. Okay, so the learning goal, determine the derivatives of polynomial functions by simplifying the expression, that one, the difference quotient, and then taking its limit. Okay, so the derivative, so up until now, we've always called the derivative either the rate of change or the slope of the tangent, but now we're going to start using the word derivative. Okay, so the derivative of f at x equals a is, okay, we use the notation f prime, that little apostrophe looking thing, we say prime. So f prime at a equal to the limit as h approaches 0 of f at a plus h minus f at a all over h, provided the limit exists. So the derivative is, which we denote f prime at a, is just the same thing as the slope of the tangent to f at x equals a, which is the same thing as the steepness of a curve at a point. Okay, so some ways to represent the derivative include f prime dy dx, f prime at x, y prime, or df at x dx. All of these different notations mean the derivative. Sorry, but they're all the same thing. So dy dx is called Leibniz notation because it was a mathematician, Leibniz, that actually created this notation. And so it just means the limit as the change of x approaches 0 of the slope formula, right? Your change in y over your change in x. So if you see something like dx squared dx, this means the derivative, the derivative of x squared with respect to x. So WRT means with respect to. So where x is the variable. So we're going to take the derivative of x squared, assuming x is the variable. It'll make more sense why we need to say that later on. Okay. So example 1 is going to be exactly what we were doing in chapter 1, but then example 2 is where we're going to get to the real fun of finding derivative functions, not just derivatives at a point. So differentiate, if a thing says differentiate, that just means to find the derivative. Okay, if you're finding the derivative at a number, so like example 1, determine the derivative of f at x equals -4. The derivative of that will be a number because you're finding the slope of a tangent at a specific point. So you're going to get a number answer, which represents the slope at that specific point. But if f is arbitrary, if you're just finding the derivative for any x, then you will get a function. So that's what we're going to be doing in example 2, is finding the derivative function. All right, so let's try example 1 first. So we have, now we can use our new notation. So instead of m, we can say f prime at x. Okay, so it's equal to the limit as h approaches 0 of, -4 plus h all squared minus -4 all squared all over h. So this is just what we were doing before. So the limit as h approaches 0 of, okay, we can expand this to be h squared minus 8h plus 16 minus 16 all over h. So again, we all know all this slicing and dicing we got to do. 16 and 16. See ya. And then one of the h's is going to cross out, okay. Got excited quick. So now we take out this h, we get h minus 8, this h, okay, see ya. So now this can go to 0, so we get -8 as our solution. So we can say that, actually, this should have said f prime at -4. That shouldn't have been an x there. That should have been a -4 since I'm finding the derivative at -4. So we can say now that f prime at 4 negative 4 is equal to negative 8. So notice how the answer is a number. So what does this mean? This means the slope of the tangent to the function at the x value negative 4 is equal to negative 8. So if you were to draw a tangent at x equals negative 4 of this function, its slope would be negative 8. Okay, old news, Mrs. Weens. Let's get on to the new exciting stuff. So what about a derivative function? So what if we want to find the derivative anywhere? We want to find the slope of the tangent anywhere, and we don't want to have to calculate it 3 million times for 3 million different points. Well, we can actually create what's called the derivative function. So basically by finding this limit for any value of x. So that is where we do f prime at x instead of f prime at a number. So that is the limit as h approaches 0 of x plus h, because we're letting it be any x value, squared minus x squared, all over h. Okay, so now we just do some fancy algebra here. It's not that bad, we just have variables. So when you expand this binomial, you get x squared, careful, plus 2hx plus h squared minus x squared all over h. So now these x squareds cross off. And then, so these x's are going to go away. And then I'll be able to common factor an h from the top. So I'll have h bracket 2x plus h over h. So now these go away. And this approaches 0. So I get 2x. So what does that mean? Well, it means that the derivative function of x squared is equal to 2x. So notice how this is a function, not a number. So that means, yay, if we want to find the slope of the tangent to x squared, all we have to do is take the x value that we want to find it at and throw it into this function, 2x. So you want to know the slope of the tangent at 16? It's 32. You want to know the slope of the tangent at 1.25? It's 2.5. You want to know the slope of the tangent at x equals negative 1,000? It's negative 2,000. Simple, easy, because we found a derivative function and we don't have to actually do the limit each time. So an alternative way of writing the derivative of f at the number a is, okay, this is a notation-y thing. You can do limit as x approaches a of f at x minus f at a all over x minus a. So that's just another way of writing the derivative at a specific point a. So now there's an investigation on page 67. Take a look at that one. You can pause the video and take a look at that. So the derivative function is, in general terms, the limit as h approaches 0 of f at x plus h minus f at x all over h. So no matter what function you want to find its derivative function for, this is how you do it. You find the slope, the limit of the slope between that x value and h as h approaches 0. Okay, so when you use the limit to determine the derivative of a function, it is called determining the derivative from first principles. As I said, this is actually the last day we're going to be using limits. And so for most of the rest of chapter 2, we won't be using first principles. So just remember that for the test and for the exam. If it says find the derivative using first principles, that means to go back to this limit definition and do it the way we're doing in this note. Okay, so now we're just going to do examples and just have the time of our lives. Okay, so example 3. Here we just have a simple square root function. Notice the variable is t, whatever, that doesn't bother us. It's just the same thing as x, just a different letter. So we're going to find the derivative function for any variable of t. So if I ever want to find the slope of the tangent to this square root curve, all I have to do is put it into the function I'm going to create. So remember, we call it f prime at t is going to be equal to the limit as h approaches 0 of root t plus h minus root t all over h. Well, what do we do with this now? Well, we have roots, so you should think conjugate. I want to multiply it by the conjugate. So the conjugate of this is root t plus h plus root t. And we got to do that on the bottom as well. So that we're just multiplying by 1. Okay, so now we got to flex our algebra muscles. Okay, so this root times this root just makes the root go away. So you get t plus h. And then you get plus this minus the same thing. So there's no middle term. So then we just have minus, sorry guys, I have a bit of a tickle in my throat. I might need to drink some water. Minus t all over. And then you don't need to FOIL this through. You just have h bracket root t plus h plus root t. Okay, so now watch what's going to happen. These t's will cross off, t minus t goes away, and this h will go to 1. So you get the limit as h approaches 0 of 1 all over root t plus h plus root t. So now I can sub in my h goes to 0. So I have 1 over root t plus root t. So you get 2 root t. Okay, but I need to give the restriction that t has to be greater than 0. So note here that the restriction on my function was that t had to be greater than or equal to 0, but the restriction on my derivative is t is greater than 0. Why do they have different restrictions? Well, because now we have a rational function. So our derivative function is rational, and we can't divide by 0, and then a square root can't be taken of a negative. So that's what I want you to write here. So just notice that the restriction on the derivative does not include t equals 0. Okay, so you can actually write this out. I'm not going to write it all with my pen, but basically I want you to notice that this does not include t equals 0. So therefore, a function is not always differentiable on its entire domain. So that means that you're not always able to take the derivative everywhere on an entire function. So let's think about why that's true for a square root function. Well, remember that a derivative is just a limit, and for a limit to exist, you have to have limiting values from the left and from the right. And at exactly t equals 0, that's where the function quote unquote starts. So there is no limit coming from the negative side. Okay, so the limit doesn't actually exist. Again, if you picture a square root function, it looks like this. So exactly at 0, we have a limit coming from the right, but not from the left. So the limit doesn't exist right at 0, which is also another reason why this is not differentiable at 0. Okay, example 4. Determine the equation to the tangent. Do a different color. 1 over x, so here at x equals 3. So in this case, you could just find f prime at 3, but I'm actually going to find the derivative function first and then just sub 3 into that function. So f prime at x is equal to the limit as h approaches 0 of f at x plus h. So 1 over x plus h minus 1 over x all over h. Okay, so the limit as h approaches 0. All right, so we want to get a common denominator here. So it's going to be x times x plus h. So we get an x here minus x plus h on here all over x plus h. I just got a common denominator, sorry, x times x plus h. So I just am getting a common denominator here. And now instead of writing a fraction over a fraction, I'm just going to write this as times 1 over h. just so it looks nicer and also takes up less room. Okay, so the limit as h approaches 0. Okay, so x minus x is going to give us nothing. And then we'll have this h being crossed off with this h. Because can you guys see that? Okay, this x minus x. And then, sorry, this will be a negative h crossing off with this negative h. So bam, 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 bam. But notice I'll still have a negative 1 on the top over x bracket x plus h. Okay, so now I can actually let my h approach 0, and I get negative 1 over x squared, where x cannot equal, x cannot equal 0. Okay, so now I want to find the derivative at 3, so I just sub in 3, so minus 1 over 3 squared is minus 1 over 9. Okay, so that's the slope of the tangent at that point, but now it wants us to find the whole equation, so I'll just change to a different color. So I know it's y equals minus 1/9 x plus b, and then I can sub in my known points of x is going to be 3, and y will be 1/3. So 1/3 times 1/9 times 3 plus b. And if you solve that equation, you get b is equal to 2/3. So your final equation is y equals minus 1 over 9x plus 2/3. Okay, so graphically, if you want to see this, you can actually graph this on Desmos or GeoGebra. You can graph the function 1 over x, and you can create a tangent line at x equals 3. I'm not sure how fast this will be. If it takes too long, I just won't do it. Spoke too soon. I am going to wait. Okay, so f at x equals 1 over x. Okay, and then I can say tangent bracket at 3 on the function f. There you go. So that's the same as minus 1/9, and there's your y value, 2/3. So it does it for you on GeoGebra. Okay, back to the note here. Okay, so let's do this next example. So find a line perpendicular now to f at x equals 3. Well, let me just get a different color. Well, we know that the slope of the original was minus 1 over 9. So therefore, the slope of the perpendicular is going to be positive 9. So find a perpendicular line there. So now our equation will be y equals 9x plus b. So we can still put in our point of 3 1/3. So when you rearrange this, you get b is equal to minus 80 over 3. Okay, because you get, when you get a common denominator, that's how it ends up working out. Okay, so then the equation of your line is y equals 9x minus 80 over 3. Okay, so now that we're more sophisticated with our math, we don't really love this. I'm going to write it as in standard form. So I'm going to multiply everything by 3. And then change it to standard form. So 27x minus 3y minus 80 equals 0. Okay, and that's likely how you're going to see equations in the back of your textbook when you're solving for that. So just remember standard form, you need all of these coefficients to be integers, and you need your leading coefficient, the one on the x, to be a positive integer. Okay? So the normal to f at any point P is the line perpendicular to the tangent at P. So if a question asks you to find a normal, it was going to be just like this question up here. It's going to be asking you to find a line perpendicular to that point. So you just need to find the slope of the tangent and then use its negative reciprocal and the point to find the equation of that line. Okay? Okay, just a couple more things. Excuse me. A function is differentiable at A if f prime at A exists. Otherwise, the derivative does not exist. There are three common ways for a derivative to fail to exist. So the first one of those is called a cusp. And it looks like this. So it looks like functions going like that and like that. So it kind of looks how I used to try to draw birds when I was in grade school. Let's be honest, how I still draw birds. So basically the function is approaching negative infinity, and here also it goes to a sharp point. So the limit doesn't exist there and the derivative doesn't exist there. Okay, another option for a way that is a vertical tangent. A vertical tangent. So basically a curve is going along, and all of a sudden for a brief second, it has a vertical tangent. Okay, so the function, it's still a function because there's not more than one point. That's one on top of each other. Okay, remember if that was true, it wouldn't be a function. But it curves in such a way that for a split second, it has a tangent that goes exactly vertical, which means the slope is undefined. And because derivative is just slope, it means the derivative doesn't exist there. Okay, the last option is a discontinuity in a function. So for example, bloop, 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 and then you have a hole, and then the function continues. So the function would not be differentiable right at that discontinuity. Okay, so it is possible for f to be continuous at A, yet not differentiable at A. If the function is differentiable at A, then f is continuous at A. Okay, so if you're able to find the derivative at x equals A, then the function is continuous there, but you can't say that backwards. So if it's continuous there, that doesn't necessarily mean you can find the derivative. For example, a cusp and a vertical tangent, at either one of those points, the function is continuous, but you're not able to find the derivative. So example 5, show that the absolute value function is not differentiable at x equals 0. Okay, so we're going to do that using limits. So the derivative of 0 is equal to the limit as h approaches 0 of the absolute value of 0 plus h minus the absolute value of 0 all over h. That's the definition, right? So this leads us to the limit as h approaches 0 of the absolute value of h over h. Well, because the absolute value is really a piecewise function, we have to do two-sided limits from here. So this is actually equal to the limit as h approaches 0 from the negative side. So that would be negative h over h is negative 1. And the limit as h approaches 0 from the positive side is h over h, which is equal to 1. So therefore, the limit does not exist, which means that the function is not differentiable there. All right, so there you go. There's your note. Basically, now you're going to be doing work where you're finding the derivative function using first principles on a whole ton of different functions, and you're finding out if the derivative exists or if it could be a cusp, a vertical tangent, or a discontinuity. So thanks for watching, guys. Hope you learned lots, and I hope you had fun.